This is Mr. Lee's physics class. I'm Mr. Lee. In the previous videos, we learned that heat is a transfer of energy from a body of higher temperature to another of lower temperature. Without any change of states, the one losing heat cools down and the one gaining heat warms up. And finally, when their temperatures become the same, heat transfer stops and the bodies are said to achieve thermal equilibrium. Then, a natural question is it possible to find this temperature when thermal equilibrium is achieved? This is often just loosely called the final temperature when we put bodies of different temperatures into thermal contact. Estimating this final temperature is the goal of this video lecture. The idea at its core for this type of problems is the conservation of energy. Assuming low heat is lost to the surrounding and no heat is absorbed from the surrounding, all heat that is lost by the hotter body must be absorbed by the colder body. So we can equate them to form an equation. To relate each of these heat Q to temperature change delta T, we should apply either Q equals mc delta T if the specific heat capacity small letter c is known for a body, or Q equals c delta T if the heat capacity capital C is known instead. Sounds abstract? Let's work on a real problem to see how this helps us to find final temperature at thermal equilibrium. To make myself a cup of flat white, I mixed about 60 grams of espresso at 85 degrees Celsius with 100 grams of milk. However, the milk has been refrigerated and is at 4 degrees Celsius only. Now, my question is, if I directly mix them together to form the flat white, what would be the resulting temperature T? Then I will know whether the flat white made this way will be too cold or just right for consumption. As I just taught, the key equation is that the heat lost by the hotter body equals the heat absorbed by the colder body by assuming that no heat is lost to the surrounding or gained from the surrounding. Then, in our case here, heat lost by the hotter espresso equals that absorbed by the colder milk. To relate heat Q to temperature changes delta T, Q equals mc delta T where C is the specific heat capacity can be used. One thing good about this equation is that the specific heat capacities of various substances can be looked up easily from data books or the internet. In our problem, that for milk and water is found here with a simple internet search. By the way, the specific heat capacity of espresso can be taken to be very close to that of water. So, after some proper unit conversions and rounding, let's take the specific heat capacity of milk as 3,800 joule per kg per degree Celsius and that of espresso as 4,200 joule per kg per degree Celsius. So, the heat lost by the hotter espresso is given by its mass times its specific heat capacity times its delta T. Be reminded that since this is a heat loss, this delta T refers to a temperature drop. Similarly, the heat absorbed by the milk is equal to its mass times its specific heat capacity times its delta T, but this delta T is a temperature rise as the milk absorbs heat. So, we have this equation. Now, the specific heat capacities and the masses are just values given above and can be plugged into this equation. Then what about their delta T's? Before moving on, I expect you to have the common sense that the final temperature T should be in between the initial temperatures of the milk and the espresso. That is, T is in between 4 and 85 degrees Celsius. This is obvious because the temperature of the milk rises as it gains heat and the temperature of the espresso drops as it loses heat. So, for the milk, its delta T rise in temperature is T minus 4 degrees Celsius. And for the espresso, its delta T drop in temperature is 85 degrees Celsius minus T. Solving this equation and manipulating the units correctly, we have this result. The temperature of the resulting flat white is 36.3 degrees Celsius. Well, this is too cold for a cup of good flat white. Probably, I should preheat the milk before it is mixed with the espresso. So, this is the basic of finding temperature at thermal equilibrium when we put two bodies into thermal contact. Of course, there can also be 3 or even more bodies instead of just 2. But the idea is just the same. It will be heat released equal to heat absorbed nonetheless. For example, if bodies X, Y, and Z are in thermal contact and X drops in temperature while Y and Z rise in temperature, then X must have lost heat while Y and Z must have absorbed heat. Then our basic equation becomes this. The heat lost by X is equal to the heat absorbed by Y plus the heat absorbed by Z. And then just like what we did before, we will associate this heat with change in temperature through either of these two equations. I'm not performing an actual calculation on this as this is too repetitive. But you can play around with this easily. Say, mix espresso with milk and also sugar. All you have to do is just to look up the specific heat capacity of sugar on the internet, and then you can start to have fun with the calculation. Enjoy!